name is Pedro Umbelino. I'm a security researcher nowadays at BitSight. I've collaborated with a bunch of different initiatives and institutions. My main line of work is not hardware, surprisingly. It's just my hobby. There's my contacts. Feel free to reach out if you have any questions or you want to discuss some cool hardware or not projects. So what is this talk going to be about? Hacking with hardware. Hacking with hardware is not hardware hacking. So we are not going to hack into a GPS tracker. We're not going to break your Samsung trying to grab your Bitcoin wallet that you forgot the password. By some of those promises, although not all, are starting to materialize in very cool gadgets that are used to hack into systems. So I want to share my experiences, my tips, my fails, especially some fails that if you're starting out, they are very painful and costly, so hopefully you will not repeat my mistakes again. I want to try to encourage to bring more folks into the hardware makers movement with a security mindset. We are more as each day passes, but there's some space. And I think one of the resistances that we had into hardware tinkering was what I call the analog multiverse. This is just something that I refer as a bunch of us, probably most of us, have a strong software engineering background, right? So it's okay when it's binary ones and zeros, but it's not so okay when we start to talk about resistance, capacitors, soldering stuff, and there's this resistance into thinking this is too hard, and people give up before they start trying. So before I get into that, I want to give a brief historical hardware device overview and its creators. I think they lay the ground for the current times of hacking. Some of them are just curiosities, and some of them maybe some inspirational stories for you. So I want to start with this guy, Nevin Maskelyne. Nevin Maskelyne was contemporary of Guglielmo Marconi. So this was around 1903. He was a British inventor, magician, and probably was the first wireless hacker, although he probably didn't think of himself like that at the time. So Marconi developed wireless telegraphy, and he had a bunch of secure and private communication claims. They had a lot of patents. Maskelyne was not a fan of patents. He had like maybe an activist mindset. He didn't like the things that Marconi was claiming he was able to do. And one of the demonstrations that Marconi did at the Royal Institution, he was demo his new technology to secure and private radio communications. So this was essentially, you cannot predict or know the frequency that the transmission was going on. So, of course, for us now, this kind of security to obscurity does not work, and it's obvious, but keep in mind this was the first days of radio, so most people didn't even understand how that worked, and in Marconi's head, you could not figure out which frequency was being transmitted, some communication, so it was secure. And Maskelyne did not agree. So what he did was that he learned when this demo was going to happen at the Royal Institution, and it was near the West End Music Hall, so he rented a house nearby. He had a lot of experience in radio. He had built radios and antennas, some of them 50 meters high, so he was not properly an amateur, although he was self-taught. So he rented this house, and when the demonstration was going on, what Maskelyne did was he started to transmit Morse code of a very dirty poem. So people in the house, they started to listen. But the audience, most of them knew how to, understood Morse code. So they started to understand something was going on. It was a dirty poem. So it probably was the first wireless hacker in this sense. So moving forward, Mary Adam Ryszewski was a Polish mathematician and cryptologist that invented the Bombe Cryptological. So this is around 1932 when the Germans created Enigma. I'm pretty sure almost everyone probably knows what the Enigma machine did was kind of to encrypt communications, right? So Ryszewski bought a commercial Enigma machine, and he was very smart. He was able to reverse engineer using just the commercial version, he was able to reverse engineer the military version. So the fun part was that, so the Enigma machine works with a set of rotors that have to be pre-configured in a certain order using the letters from the alphabet. So the commercial version was like the QWERTY, it was not exactly QWERTY, but configured like the QWERTY keyboard. And it was trying to understand, this was fundamental to the crypto communications, and nobody knew how the military one was configured. And the British were working on this, and it just decided to try every combination, and it started, you know, at the alphabetic order, A, B, C, D, and it worked at the first time. So the British didn't try this combination because they thought it was too obvious. They didn't even try to break the first Enigma machine like this. So then he produced kind of Einstein of, Frankenstein, sorry, of 6 Enigma machines, and he was able to break codes in real time. Then the Germans found out, it stopped working. Then came along Alan Turing, a man that did too much work for us to start talking about all the things that he did. We are probably here because of him having this conversation. He developed the Bombe that was based on the Bombe Cryptological with some help from Welshman, and they were able to decrypt communications in almost, well, real time. For the time, we can call it almost real time. It was practical to use, and it was fundamental to win the World War II. Moving, again, just hardware that was made with the specific purpose of hacking into stuff, in this case in the cryptology field. Now, for the older guys here, probably they know who Joe Bubbles or Joe Ingressia was. He was a famous character. He didn't kind of invented any hardware. I think he was born with a hardware built in. He was born blind. He was very interested in playing with telephones at the time, and he discovered that by the age 7, he discovered that he could whistle into the phone and control the telephony network. So he was actually able to dial just by whistling a perfect pitch. So this was a precursor for a very prolific period for a specific set of hackers back in the days called phreakers. And hardware making was involved. And I just want to quickly share a video with you of him. Oh.
In the days when calls went through to operators,
There's no
phone
sound.
phreaking wasn't possible.
Can you hear?
But as human switchboards were replaced by mechanical systems, different noises were used to trigger the switches. If you had perfect pitch like blind phone freak Joe Ingressia, you could whistle calls through the network.
Let's see if I make it this time. This is really hard to do. It sounded like all the tones were present, so the phone should be ringing about now. Okay, it hit the phone. It just takes a little while.
He even showed off his skills for the local
So
From his one phone to a town in Illinois and back to his other phone.
let me put this off. So, yeah, the hardware was built in, but I like to talk about Joe Bubbles because he was in the origin of a very, very prolific hardware hacking and making period. So in the 70s and 60s, it was the golden age of phreaking. Phreaking was essentially phone hackers, if you will. One guy, very famous also at the time, called John Draper, or Captain Crunch, he was kind of into it, but not much. There was a group of also blind folks that were doing the same thing as Joe Ingressia, but none of them have electrical engineering background. And they talked to John Draper, which had an electric engineering background, saying, look, we are whistling or recording sounds and then playing them back to the network. And if we could just have some kind of device that we dial in and produces the exact frequencies that we want, it will be much easier. So it was a period where boxes started to appear, like the blue box, the red box, there's a lot of boxes. It was essentially each box had a function, how to hack into networks, like placing long-distance phone calls and you wouldn't pay. At the time, Phone calls were very expensive, not like today. So again, a lot of hardware that was made just for the purpose of hacking into systems. Now, moving a bit forward, Van Heck, if you heard about Tempest, which is not exactly, it's a specification, but this guy was in the origin of that word, so to speak. So he invented this device, which essentially he could point an antenna to any CRT screen and have the screen being reproduced in his own screen. So he could see what was on a computer screen 100, 200, 300 meters away. So it was deemed not possible, but he proved it was possible, very cheap and almost off-the-shelf components. So then if we move forward to 1998, we have the deep crack that was a piece of hardware specifically designed also to break into cryptography. In this case, the purpose was to really demonstrate that DES was broken and should not be used. It was known by the cryptologics community for a long time, but this was the demonstration in practical use that it was not safe. So several things were happening in this period. So the internet kind of was born. So the community started to gain strength and share knowledge on the internet. Vendors started to produce more accessible devices and cheaper. There were the PICs, the basic stamps, the AVRs. They were very commonplace into building lots of hardware projects. And then came along websites like eBay, and Alibaba then paved the road for very cheap components. So it was getting more and more accessible to start to play around with hardware. At the same time, the hackerspace movements were kind of growing up in a lot of different cities, and Arduino was created. Arduino was, if you look back, a very important tool because kind of crystallized some of the stuff that the teachers want to teach. So it was a great platform to teach. Later, Raspberry Pi did the same. Now we have ESPs and other chips that, you can connect everything to the internet nowadays, which is sometimes not a very good idea, but people keep doing it. And then there's a lot of online PCB maker services that you can actually order your PCB. Sometimes you can actually order for them to be assembled at a price that is not prohibitive. So that's why I think today we live in privileged times for hardware hobbies. There's abundance of online information. There's community. The hardware parts are cheap, and you can just buy a starting kit of wherever piece of technology that you are interested in, solder it yourself, and kind of learn how that worked. And we saw, since 2019 till today, there's a lot of new devices here that did not exist. I think in 2019, I think everybody knows that those eyes and faces, the Panagotchi. Nobody talks about Panagotchi anymore because we have a new mascot, new aquatic mammal that people, some have already and some are still waiting for it to arrive. The Flipper, which is a great tool. So this was kind of how we get to today as a community. For me, for myself, it all started with that little guy over there. Actually, that one, but I had a Spectrum when I was 8. I wrote my first program when I was 10 by reading the manuals. Then I got a PC rather late. I was 14 at the time already. And of course, I got my first computer virus. And this was kind of what started it all. I had a friend of mine that asked if 2 disk drives were near to each other, if the other one would become infected. Okay? I knew it wasn't possible, but I also could not explain to him how do viruses propagate, how do they work? And that question was in the back of my mind. Like, I think the analogy that we chose for virus makes sense for us as a community, but for the people that have no info knowledge, information technology knowledge, for example, they think it works like a normal biological virus, right? So it's a valid question. So I bought an assembly book, and I started to reverse engineer Barotas until I understood how it worked, and then I learned Pascal. Yes, I know Pascal. by 16 years old. It was what I had, and then the internet came, and the internet changed everything. A lot of knowledge was accessible. You can start to source for parts and learn new stuff. And actually, in the university, I found this device still in my house. It's completely full of rust, but that was my first decent hardware. It was a 256 bits memory that stored an encryption key. And I wrote some programs. My computer will need this to unlock itself. Of course, it had batteries inside, and it was volatile memory, so when the batteries died, I had to format my computer. Still, I produced more gizmos, mainly to interface with payphones and stuff like that I will not share with you in this talk. And then I built some other stuff. And what I always try to do is I don't have an electrical engineering background, so to avoid the analog multiverse, what I try to do is figure out modules, how do they work, how do they communicate with each other, and bring whatever I want to do as fast as I can to the digital world, meaning if I can, I will implement a filter using software instead of capacitors. I know it's not right to do, but since I'm producing a prototype, I can do it, and if it works, and if I want to make some product to commercialize, for example, then I will talk to an electrical engineer, and he will help me figure out the perfect solution. But you don't need to worry about everything when you're just producing a prototype. Just make it happen. Especially if you just read the fine documentation, you'll find a lot of information about every chipset nowadays, and you take your time to read it, and you can interface almost everything just by yourself, if it's not very small to soldier, but we'll get into that. So I'm going to share my hardware building approach. Like, your mileage may vary. It's my approach. It's as valid as another, I guess. It works for me. And usually it has a bunch of phases. So, of course, there's a motivation when I start some project. I'm going to base this second part of the presentation on a device that I'll build called IO433. There was some motivation behind it, why I started to build the thing or thinking about building. Then I tried to properly define which features and how I want this project to look like. And you do a bit of research, which models can you use to implement the functions that you are looking for to make it work. Then you get to the design part, where you sit at your computer, you actually design the PCB and the computers, you source the parts, fabricate, test, and just loop it and try to figure out what went wrong, because things will go wrong, of course. So for this particular project, my motivation was, as usual, necessity. I lost my garage door opener, okay? So, yeah, I think of myself as a hacker, so why would I buy a garage door opener very expensive, like 40 euros, when I can spend a lot more money trying to build one myself? So, yeah, I always had this urge to hack into this kind of devices, like door openers, sensors, and things that work on the 433 megahertz, so this was the perfect excuse. And then I think, okay, if something cool comes out of this, I can publish the code, like share the code, hardware, my results, and stuff like that. But I was just trying to build a remote, okay? So this was not IO433 yet. Then I had some issues. To reverse engineer the remote, I had to understand how frequencies work, and I had to sniff the transmissions. And I could have some tool that could, make my job easier. Then I start to think about and learn there's a lot of applications that usually use this particular frequency to communicate, like anemometers, remote keys, thermometers, I don't know, wireless plugs, weather stations, whatever. And maybe if I have some kind of multi-tool that for 433 that helped me, I could develop a remote faster. So the IO433 was born at the same time I was trying to clone a remote. It was not a remote, it was something that I wish I had that will help me build the remote. So I built this both at the same time, kind of. So essentially, when I get to the definition, I said, okay, I want a sniffer that can store, replay, dump, and monitor signals. It would be cool if it had some other features, but this is where I want to start. It has to be able to replay and analyze signals. So that's the way I can build another garage door opener. So that was the first features that I want. When I started, I know there were some projects that could do similar things. You could use software-defined radio to analyze signals and replay it with your computer, for example. And there was a promise at the time, because this is not a new project, that a new, like I said, aquatic memo, the Flipper, was going to be born. I'm not sure if they started the Kickstarter campaign just a bit before or after I started this project, but it would take a long time, so I just did it myself. So in the research phase, as I was saying, I just broke down the project per functionalities, and I searched for parts that could perform whatever I wanted to do. So I wanted to be able to sniff and to replay. Is there some particular chipset that already does this? How can I interface with this chipset? And so forth. And if it is easy or not for me to implement it myself, or should I use modules instead of trying to design the entire thing? And of course, reading the documentation helped me. I also did a bit of research about how signals work in the 433 megahertz bands. Like, are we talking about modulations like ASK, FSK? ASK is amplitude shift keying. It means that when there's a signal being transmitted, it works a bit like Morse code, if you want, or imagine a light bulb going on and off, and it's the transmission being kind of transmitted, sorry, and radio silence. And that's amplitude shift keying. There's frequency shift keying. So I had to kind of reverse my own remote and figure out which one will I be using. So the functionalities: read, write, 433 megahertz signals. I want it to be portable, ideally with a battery and a graphic user interface. I want to be able to store signals and to connect to the PC and decode the signals in real time if I want, and not in the platform. You can see the upper side is the remotes. So the remotes that I was able to clone. It was based on the FS1000A and other chipsets. But they were kind of not enough for what I wanted to do with the I/O. They were enough to open my garage door, but not to sniff all signals. So in the bottom side, you see the very first prototype with the TI-CC1101, which is the antenna one, and then the SP32 with a small display. So, research. Now I knew what I wanted, well, before building the actual device. When you're into this part, you should elect your electronic design automation software. So this is essentially the software where you design the schematic. And usually you design the schematic, and the software itself is able to also produce the board and the copper traces and so forth. There are several available. There's Eagle, there's KiCad, there's commercial programs, there are free ones also. You should, if you're starting now, you should try a very small project like LED blinking and design it from zero to having the actual board produced. And understand which one do you want. I don't have a favorite. I use usually Eagle because I started with Eagle. They are not very user-friendly. I don't think they are. There's some stuff that takes a lot of work to learn how to do in one, and if there's changes in other piece of software, I don't want to lose a lot of time just learning a new EDA, so it will be wise to select one first. Like Eagle has a free version, but it's also a paid version if you want to build bigger projects. And for me, I should probably have thought about this advice before choosing Eagle, but now it's too late. So choose your parts wisely also. You have to decide, are you going to make the PCB? Are you going to order the PCB? Like if you want to actually etch the PCB yourself, or are you ordering the PCB? Are you going to hand solder it? Are you going to order it, assemble, and spend a bit more money? This is all decisions in the design process. So last year, last B-Sides, I presented very more complicated project than this one. This is super, super simple if you want to start soldering stuff and in the end have a very cool device that can hack into garage doors and stuff like that. So it's essentially just a PCB board. So it was designed in Eagle, and I didn't have to worry about package types or SMDs, or I just had to worry about the design, which is essentially keep it simple. And I did. It's a breakout board where you can buy 2 modules, you solder the 2 modules together, and it's done, and it's working. And you can do a lot of interesting stuff. So, but if you're doing more complicated stuff, then you have to worry about package types. You have to understand the difference between a DIP, for example, package type, and KeyFN. And if you look at your badge in the back, you can kind of see the spacing differences if you want to hand solder those components by yourself. Some of them, in the design phase, if there's a chip available, for example, in different packaging types, you should be wise and choose one that you can actually hand solder if you're going to do it yourself. Otherwise, you're in trouble. Then, there's a lot of them. So, then you have to know about S&D sizes. If you're using some analog components like resistors and capacitors, you should look careful before you order, because there are some sizes that in the metric code and imperial code, the code is the same, but the sizes really, really differ. Again, if you look into your badge, I once ordered a full reel of 0603 components that I was going to hand solder, but instead of ordering imperial, I ordered the metric one. And if you look at the size of the 0603 metric one, try to solder that by hand. Good luck. So be careful when you're choosing components. Then when you're designing, choose a EDA that has auto root. Every EDA nowadays have auto root. Auto routing is just the translation of your schematic connections into the copper traces. So if your project is small enough, you can do it by hand and optimize it by hand. It's fun, but it doesn't have to grow a lot, so it becomes impossible to actually route all the wires by hand. So yes, in this case, on the middle, it's the IO433. Here on the right was the 2019 project. It was a bit harder to route by hand. It was called Uberhead and had a bunch of neat features that I talked before. So in the end, this was the PCB. Advice: double check before production. You can see here there's a version 0.1 and 0.2 because, again, I failed to listen to my own advices. And so I wanted to support more boards and quickly found out that I produced and ordered a bunch of PCBs that were not compatible with some of the more accessible chipsets that I was using. So I had to do everything again and make another board that now has this on-off jumper switch, which what that does is it actually supports, like the device here, so it actually supports different modules just by, you just select a solder jumper there. You can choose between 2 models. Some of them are easier to find than the others to control the 433 megahertz communication. So, and then you just burn a different firmware. So when you're sourcing the parts, choose your vendor for the PCB and components. Sometimes they sell just the PCB. Sometimes you can, in the same vendor, you can order the PCB, the components, and the assembly all in one. There are some cool ones and very accessible nowadays. Usually the shipping speed versus money is important because most things come from China, and PCBs tend to be heavy. When you're just designing one, it's not heavy, but for example, the badges this year were 13 kilos of badges. So that costs a lot when you're shipping, right? Be careful when choosing components. Be thoughtful about future availability of the parts, which was a problem for this because the IO433 the parts that you need for it are still available, but you see there's another version of the chips being produced, so it's harder and harder to find a specific version that supports the same pinouts, for example. And in projects that make sense, get this PCB stencil. The stencil is that metallic sheet that's perforated with the right sizing when you're hand soldering small components. So essentially, you put the PCB board below, and you put the metallic sheet above, and you spread solder, and then it becomes a lot more easy if you're soldering very small parts. So you don't need high-tech or expensive gear, you just need to practice. Myself, I usually travel with one of those soldering irons that it's gas-powered, so you don't even need electricity, and you can just, by unscrewing the tip, it becomes a hot air gun, so it's 2-in-1 and super cheap. You can order these starting kits just to try and practice drag solder or hot air solder. Other than that, you need a multimeter. If you want to spend a bit more money, you can order an oscilloscope like this one, which is also cheap, around 150 euros, I think. And infrared thermometer, if a lot of things start to produce smoke, don't touch it. Like a burn chip can go up to 500 degrees, so your skin will just slide off when you touch something very hot. I know how that goes, fortunately. So, yeah, then you come to the testing phase. You just figure out if things start to go wrong. Just iterate the process. Start by going to the schematics to see if there's a routing issue, or if you choose the wrong combination, or you connect the pinout somewhat wrong. If everything is okay, then go to the PCB to see if the copper traces were badly designed, and start to test each connection for conductivity. So there's a bunch of work involved that it's in the testing phase if things don't work at first, and they won't, I'm sorry. It takes some time and practice for things to work. So this was kind of the evolution of the I.O. On the upper left, you can see the remotes that were Arduino-based, and then the evolution into something with an ASP that has a screen, so I can actually program a graphic user interface. On the upper right side, it was a very small. It was actually the remote for my door, and then the first prototypes, and then the prototypes that had like a 3D casing that you can download. It's all on GitHub. You can actually solder and use a case like this, put a small battery, and you can go and hack garage doors, but please not mine. So this is the final revision. I already talked about some mistakes I did with the PCB, the green one and the black one. So I have some here. So essentially what IO433 prototype become is an open source ESP32 and CC1101 based sniffer. It has Bluetooth low energy and Wi-Fi capabilities. I'm not using it now in this firmware because I'm waiting for very smart people like yourselves to come join and help me with the firmware. You can order the parts online. You just solder some wires, or you can actually order the PCB or ask me for one PCB to solder it yourself. I have some if you want. And then 3D print a case, and it looks very professional like this. So, yeah, feel free to join in. I will try and make a demo. I wanted to bring my garage door, but it's too big to fit my car, so I'll just demo it with a doorbell. I know. I'll just connect this Bombe radio so you can also hear hopefully, if Murphy laws allow. Okay. So what I'm going to do is I'm going to replay the signal and record it here. It's hard to see. I cannot show you, but trust me, I will not press this button. Now, recording. and replaying. No. Wait, I have time. We'll do it again. Replaying. Also no. Okay. Well, I have a lucky charm here, so I'll try and copy it again. Okay, it's done. Oh, shut up. And again. Yay! So this is just a replay. No, you can stop. This is just someone is using. I know. Thank you. Okay, I could detect it here. Like it says Flipper Zero being used to screw up your presentation. So, yeah. So this does a lot more than just replaying. You can actually connect it via serial port to your computer, analyze the signal in real time if you want to have some scripts running or detect spoofed signals and things like that. Or you can just use it to play around and also ruin other people's presentations. So essentially, this is what I wanted to share with you guys. I think we live in a fantastic time to tinker with hardware. Anyone can make it. You don't have to make very complicated projects nowadays with the amount of different chipsets that we have available to really produce useful devices and prototypes that you can use while hacking. I think we are getting our own promised Hollywood-style gadgets, and there's so much more to be invented if we just have the courage to invest a bit more into hardware making and take that step. Please join in. I'm sure you can do it too. So, thank you. Oh, this is also a hardware device. Yeah. Questions?
So thank you very much, Pedro. Any questions? Still have quite some time. So.
Okay.
There's one question here.
No. Stop.
Hello, Pedro.
Hi.
In terms of financials,
Yes.
what are we talking about? A prototype like that?
Yeah, so the components for building one prototype, like the last time I saw, the Chinese parts kind of really got a lot of expensive nowadays. Probably they grew by 100%, I guess, the price. But let's say the TTGO goes around for nowadays maybe $20, and the CC1101 goes around for maybe 5, so 25. And then you buy a battery or use a battery of another device. So all in all, I'll guess you spend like $30 building this. It was much cheaper at the time when it started. If you want to order the PCB, then it's probably better if you join with some friends and order some bigger and bulkier order. But there are websites that support makers, and you can actually order like just 5, and they ship it for $2. And if you just ask for 5, you can get very low prices. Yeah.
Okay. Thank you. Cheap fun.
Yes.
More questions? 3, 2, 1. Yeah, where? There's somewhere. Ah, here, sorry.
Hey, Pedro, awesome presentation, thank you. Would it be possible to use something similar to a breadboard instead of just going out and print a PCB?
Absolutely. The reason you want to print the PCB is that when you print the 3D case, it just slides into it. It's the only reason. You can, in this project, which is a very simple project, you can actually solder the wires or just use a breadboard, and it's the same thing.
Okay, perfect, thank you.
Anyone else?
Any more? One.
Pedro, great presentation, thank you. And what other device do you know that talk in that megahertz or hertz that you already had fun with?
That I had fun with, yeah.
If you can tell us.
Yes. Well, doorbells, they do it, like garage door opener doorbells. There's also, in the agricultural sector, there's a bunch of devices that are based on 433 to monitor the growth of trees. In particular, I know about a big olive tree plantation that uses this to monitor the growth and the watering. And of course, it's completely insecure. You can ruin an entire crop just by watering or turning off the water. This device has a quite powerful antenna, so yes, it's a field that is not being very explored because I think everyone assumes it's just broken. But yeah.
Thank you.
One on this side.
Thank you, Pedro. Just one question about the IO433. Do you have some roadmap or evolution, things that you wanted to do more that aren't currently being implemented or something like that?
Yes, absolutely. My roadmap is coming to B-Sides to share this with you, and hopefully people will help join and develop for. No, I don't have a particular roadmap for this. It was a hobby project. It can grow or not if the community is interested. I'm not planning in commercializing or whatever. The plans are available. They're online. Like I said, I ordered a bunch of PCBs that I can give some, and either things go from there or not. There are commercial available projects nowadays that do kind of the same thing. This is another one if you want to understand and play around and develop for your own personal growth, because there are some things that maybe you cannot do with other people's firmware that you can do with this. So, yeah.
Thank you.
Anyone else? Okay, I guess that wraps it up. Thanks again, Pedro,
Thank you
for everything and your talk.